Okay, so it's our great pleasure to welcome here for this PMMC2 seminar, Johannes Kleiner from LMU, who's been doing a great job with his colleague in organizing conference in Oxford and elsewhere about mathematical model of consciousness. Very inspiring. And he's going to talk today about structural computational phenomenology. Go ahead.
Yeah, thanks very much. So hi, everyone online. Hi, everyone in the room. It's a great pleasure to be here. So just a quick disclaimer. So I think most of you know this probably, but I learned that this is a very unique format where we can basically really go into depth and discuss, and where it's not supposed to be like a rigid talk as usual. So in that vein, I will also present something in a slightly usual format. I will really take my time. It'll probably be a bit long. You can interrupt me at any time. And I also, like, just to give it a go, I changed the title. So the title is now Foundations of Computational Phenomenology. Anyone online? So I've got the screen here too. I can see you maybe sometimes. If you're frustrated, just activate your camera and look like this. Or if you have questions, I should probably see that. Yeah, wonderful. Okay, so thanks for being here. So I would like to start the talk by basically asking the question, what is computational phenomenology? And can we just do a raise of hands real quick? Like, who knows what that is, or who has a good understanding or feels they're okay with it somehow? Nobody in the room? What about the people online? Oh yeah, there's Ken, of course, yeah. Cool, okay. So basically, I want to do something which is a little bit of an introduction, but it's not just an introduction. It's also already part of the message that I'd like to send before we go into the details. So basically, the fundamental idea is that computational phenomenology is a way of relating phenomenology. So I'll write it maybe in color here. That's a small p. So the small p, phenomenology. And that's really, in a certain way of understanding, it's just another word for like maybe conscious experience. Or some people use words like phenomenal character, or what it is like to be. So all of these,
Write bigger.
I will write bigger in the next thing, yeah. So that's something. So in a way of speaking, like it's just what I experience right now, the totality of feelings, thoughts, impressions, but then also the way experience constitutes itself. And I'm just going to indicate this here by drawing this little table here, maybe, which some of you are sitting, and like here's Ken, here's David, and here's Sean, and they're trying not to fall asleep. So that's phenomenology on the one hand. And computational phenomenology is the idea to make a relation between phenomenology. Actually, I'll probably draw that a little bit more. Oh, there it is, yeah. Need more space for other circles in a second. So the idea is basically computational phenomenology means somehow describing phenomenology by computational tools. So just to have a picture in mind, I'm going to draw like a little sort of physical quasi-model of the Turing machine. Maybe that's something you could do if you're sort of an old school computational phenomenologist. So this means computational tools. And there's basically a bunch of different ways of understanding computational phenomenology. This here's computational phenomenology. Oh, there's Grégoire. Hi, Grégoire. And there are various kinds of ways of understanding what computational tools are. For example, there's this original way. I was hoping to have a little bit more space, so let's see how that goes here. Well, maybe I'll just draw it up here. So there's the original way of understanding computational phenomenology, which goes back to a paper by Harlan in 1984, I think, or was it 87? No, 84. Where the idea is really sort of we use the tools from computer science, yeah, to basically describe or explain or relate phenomenology. But then, of course, there's a newer version. So this is, I'm just going to write maybe here Turing machine. This is the sort of old school computer science stuff. Or you could also say like any computational tools. But there's also a more novel understanding of it, where we basically want to make use of the computational tools afforded by predictive processing or active inference. And in that way, so if we try to represent the newer version, so that goes back to a paper by Maxwell Ramstad and Emil Seth and many other co-authors on that paper. And in a sense, what the idea is here is that instead of using the classical computational tools, we use the tools that predictive processing, active inference offer us. So for example, we could use the tools that Sean described in his talk yesterday. Yeah, so I won't draw it in detail, but the idea would basically be that we have something like a generative model here where we could sort of, where we describe what's happening according to predictive processing or active inference. And in that talk, I will say lots of general things, but I will mostly have this version in mind, which is, I think, the one most people here are currently interested in. And so maybe just to emphasize again, so this is phenomenology with a small p. So let me maybe also define phenomenology with a large p. So basically, with a small p, it denotes conscious experience, roughly speaking. Yeah, phenomenology with a large p denotes some sort of thing we can do. Yeah, an enterprise or some sort of practice we can do. And a minimal definition would be something like phenomenology is the study of phenomenology with a small p. And when I say studied, it really means sort of a rigorous study, yeah? Rigorous. So lots of emphasis is here. This is missing a whole lot. Many people, there are various different ways of doing phenomenology. So for example, I mean, there's this whole tradition which goes back to Sartre and Husserl. So maybe Husserl, Sartre, Merleau-Ponty, Heidegger. Who else did I have here? Yeah, let's just keep these three. And of course, they would add to that definition. So in their sense, phenomenology is that they have a specific interpretation of what rigorous means, and they have a lot of metaphysical ideas they want to do it as well. But in that very general sense, which I think is a justified sense, another way of doing phenomenology is really just sort of philosophy of mind. In both the analytic traditions and some of the continental traditions, they too study phenomenology with a small p, which is conscious experience. And then third way, basically, of doing phenomenology, so I don't know if you can see this, so these are just giving you a little bit of flavor about what it is that we're discussing, really goes back to what you could call the science of the mind. Science. That has been part of many of the more religious traditions from the start, like Buddhism, but also Hinduism and many others. So what I'm saying is basically phenomenology conceived like that can be done in various different ways. And usually there's not a lot of talking between these ways, but we can discuss, or like part of that talk will at least, introduce you some way of relating these things. Okay. So this is basically the very general idea. We want to do phenomenology in that sense over here, which means studying conscious experience, and we want to relate that to computational tools. And the first question I want to ask is basically, how do we do computational phenomenology? How to do computational phenomenology? And there's an answer to that, which is, I should probably add an RN here for right now. There's an answer to that, which is also in parts at least, a criticism I want to sort of put out there. I think what's currently happening basically, so let me just add this phenomenology over here, like with a big P. So this is basically phenomenology is what kind of studies conscious experience. And I think what's happening right now is that we basically use phenomenology in that sense of a practice to get words. That's, of course, I mean, a bit unfair. We could also say concepts. Yeah, and there's lots of these things. And we do phenomenology by use of concepts, and then we somehow have to translate these concepts into math. Yeah. So basically, I think this doesn't fit as nicely as I would have hoped on the blackboard, but you're getting the idea. Like right now, in order to establish the link between phenomenology and computational tools, we're basically just saying using words, and then we're saying, well, these words need to be understood in terms of math. And of course, we can ask, like, how do we do this actually? How do we actually represent these words in terms of mathematics? So let me add a big question mark here. And my claim would be that most of the things that's happening right now, I want to be very clear, it's very good. They're excellent ideas, but most of the methodology to translate these words into math right now, they're either based on intuition or they are alternatively based on analogies. And I think that if we want to build a rigorous science on top of computational phenomenology, if we want to do something that Ken and David and Gregoire also, but I meant the paper with the mathematician, Danielle, yeah, and Gregoire, if we want to do what you guys want to do, which is really sort of, and I think that's a wonderful vision, kind of replacing part of the old phenomenology with mathematical tools, we need a more rigorous foundation of how to do computational phenomenology. And the goal of the first part of this talk is to make a proposal of how this would work. But before I do this, I wanted to do a little bit of clarification work too, in order to sort of distinguish this from yet another step. So this is computational phenomenology. It means taking computational tools in order to describe or model phenomenology. There's another step that we often do, which I'm just going to draw in here. And that step is what, on my view, we would then call sort of a theory of consciousness or a model of consciousness. So a model or a theory of consciousness is a hypothesis about how conscious experience, on the one hand, and the subject matter of the natural sciences, most notably neuroscience, relate. And sort of that is a step that happens once you've done computational phenomenology. And what it means is basically you then use a description of the brain or other things. Just going to talk about the brain here. In terms of the very computational tools that you already employed. So for example, if you were to use predictive processing and active inference, just to give you another little diagram from Sean's talk, you know, this would be like, this just symbolizes the very large sort of both parallel and compositionality of predictive processing in the brain. But that would be sort of making a relation between the computational model of phenomenology on the one hand, and then the actual description of the brain in terms of these computational tools. And that is what I think is the actual theory of consciousness or model of consciousness. And my claim would be that all of these, first of all, these two steps are often made at the same time. And I think it's better to just do one after the other. Let's first think about what the phenomenology tells us in terms of computational tools. And let's then subsequently think about how these computational tools relate to computational models of the brain. But the actual purpose of my talk is another one. I'll tell you that in a minute. I just need a second to see whether I said everything that I need to say. Yeah, maybe just one thing. I kind of said this already. So the idea is that this and this is usually supposed to be on the same type. You can do another step where you basically ask what is the neural implementation of that. That's another sort of way. This is the same theory on a different level of description maybe, or class of theories, but yeah, okay. So the message is that right now I think we do these two steps together. Not always, sometimes we don't, but my claim for the purpose of this talk is that actually already in going from here to here, there's also two steps that are hidden and that are basically carried out at the same time. And this is, if you like, the third tiny little section of my talk. Oh yeah. So this is basically computational phenomenology. My claim, computational phenomenology is actually something else, and it's actually mathematical phenomenology. And I'll tell you what mathematical phenomenology is just in a second. I'll tell you how I think it should be done, but I should give credit first to people who push that. And in the context of in which I'm working, the credit really goes to Robert Prentner and Jeffrey Yoshimi, who started to do this mathematical phenomenology in a more contemporary novel sense. If anyone else has references, I know there are some people in Paris and in France who started to do this earlier. Please let me know. So in a sense, what the idea is here when we do when I say computational phenomenology is mathematical phenomenology, the idea is actually that there are two steps that happen at once. And the two steps are basically the translation of phenomenology right into computational tool is basically that would at least be my claim. It's basically a translation of phenomenology into mathematical structure. So this is basically just math. And then the making sense of this mathematical structure in terms of computational tools. Now so this is getting a little bit crowded here, but what I want to say is that basically what we have to do when we do computational phenomenology is basically we have to understand how we can use mathematics to represent or describe conscious experience. And so basically mathematical phenomenology is the question how to represent or describe phenomenology in mathematical terms. Yeah. And that is, in a sense, it's the exact same question. It's the same thing as basically asking, what does it mean to say that phenomenology has a certain mathematical structure? And this is why I renamed the talk. So this is basically, if you like, a foundation for both computational and mathematical phenomenology. It is a foundation for all the work that's happening in the field, on my view. Like, for example, so let me just say, so for example, I mean, there's a huge number of things that are happening. I just wanted to name a few. For example, there's the idea of understanding here in terms of words first, the concepts of apprehension, the intentional process of basically understanding how the objects of conscious experience, the noemas, are built from the raw heuletic data, according to Husserl. In Harlan's original paper, he wants to basically use theory of mind and understand that in terms of Turing machines. In Robert's paper, there's intentionality and basically self-worth distinction. In Ishan Singhal's paper, there's the structure of time. In Ken, David, and Gregoire's paper, there's lots of stuff. Projective geometry, the distance of oneself from oneself, ego centers, phenomenal totality, elusiveness of the point of view, the whole topic of the pre-reflexive self-consciousness. And what I want to do is basically, in this talk, is first, I want to basically explain the question of, did I write the question down? So this is basically the fourth question. I want to explain how to do mathematical phenomenology. And that is not a tutorial, but it's basically a question about how do we define things that provide answers to this question. So it's about a definition of, if you like, what renders a statement that phenomenology has some mathematical structure true or not. But it is also at the same time, if you like, a methodology in the sense of a collection of rules or procedures and concepts that you can use in order to do this. And what I'm proposing, so the goal of the talk is really, so let me try to state it again. 3 goals. First goal is explain this result, which I think could provide a foundation to what people are doing here, but also a foundation to some of the other parts of phenomenology. Second, to provide an example, so just that you can see how it works. And third, I then want to engage in a discussion with you. And I want to talk, and I think it's better if we do that at least off record. Like, I mean, we could still be on Zoom, but talk about pre-reflexive self-awareness or pre-reflexive self-intimacy. We could talk about like the specific P3R model, you know. All of these things are claims about phenomenology, and we need some sort of methodology or definition to make sense of whether any such claim is valid or not. So that is the goal of the talk. And I'll just check whether I forget anything I wanted to say. And while I do, I wanted to ask if there are any questions at the present point.
I find it very clear.
Very clear?
Mostly agree with it. The type of view more or less articulated, but with the budget.
Yeah.
With the why.
Yeah.
Kini has can really for some
network
issues. So
okay.
So maybe I guess we have questions for you back and you have anybody else in the room have questions from that? No, and online.
I think Sean has a question.
Oh, well, you just dropped down, but it doesn't matter too much. But it's just about the way you see the model of consciousness. It was just linked. There was just a connection between the sort of low-level implementation, I guess, diagram and the computational part, right? But I suppose both of those are just computational things that don't actually involve phenomenology. So I would guess for that to really count as a theory of consciousness, it would. I don't know. It doesn't feel like it's just an arrow between those two things, really, right? It includes like an interpretation of at least the computational part in terms of phenomenology itself, right? Yeah. Would you agree? So it only really makes sense.
I would kind of. So I think that generally speaking, a model of consciousness is trying to establish a hypothesis about like phenomenology or conscious experience, and the subject matter of the sciences. And on both ends, it will involve representations. And the current state of development is such that we have to say that these representations are representations of phenomenology on the one hand and physics on the other hand. Ultimately, that might not be required, but right now we need to say that. Yeah. We have no representational way of picking out the subject matter of either of the two, which is another way of saying there's no definition of consciousness. Yeah. And so, but what I really care about is like, I think that there's very often we're trying to do computational phenomenology, and we're basically thinking about the implementation in the brain. And as we discussed earlier, there's lots of different agendas in here, and all of them are 100% valid. And depending on what you want to do, that's totally fine. But if you want to be very fundamental and really strive for rigorous, very, like sort of very conservative, is this really true sort of thinking, then it's very important to say that there's at least 2 different tasks involved. The first task is to understand what are the conditions for the truth of a formal statement about phenomenology. And the second task is how does what I just found then relate to formal descriptions of the brain that happen on all sorts of levels. And I wanted to say one thing. It's good that you mentioned this, which I kind of forgotten just a second ago. So the big promise, of course, and I think that's wonderful in your paper, Ken, with like, as I said, I mean, instead of preparing the talk on my travel here, I basically just spend all the time reading your paper about the pre-reflective self-consciousness thing. And I think you have this vision too. So the vision is really that at a certain point, we can go beyond the phenomenology in terms of words and really do a proper phenomenology in terms of like mathematical concepts and structures. And this resonates very strongly with both people who are trying to develop new conceptual tools in the science of consciousness and people that are basically discourse eliminativists that are saying the concepts we have right now about consciousness don't really work. We need better concepts. So the idea would be that, mathematics can basically deliver that. There was another question. Yeah, go ahead, please.
Clear, but from a philosophical and phenomenological point of view, I had this question. I just want to know how you deal with it or think about this, because when you talk about phenomenology
Yeah.
and conscious experience,
Yeah.
always human conscious experience.
Mhm.
And when you want to talk about human consciousness experience or consciousness, it is, at least in the realm of domain of phenomenology, traditional phenomenology, it is subjective consciousness, and it is almost always, like I think it's always embodied consciousness. And these are the two big problems that's very hard to mathematize.
I think, yeah.
I just want to know how
Mhm.
you think or others
Yeah.
try to approach this or
Yeah.
Reformulate the questions.
Yeah.
Make sure that everybody can.
Yeah. So I'll try to. So if I understand correctly, you're basically asking how can we mathematize something as embodied, lived, subjective experience? Yeah. And I would answer that, first of all, like, let's get back to that. Please ask again if I forget to get back to that, because I have concrete answers. But like on a general level, I think this is a very common thought that I encounter a lot, but it's based on a conception of mathematics, which on my view is not true anymore since 1900. It's based on a conception of mathematics that's perceived as very much tied into numbers and, like somehow into numerical things. Mathematics is really just a way of talking and analyzing structure. And it's a language that can be applied, first of all, on the subjective level, just as well as on the objective level. It's not more objective than normal words, right? It has advantages and disadvantages compared to normal language. And then I would even add that mathematics, on my view, is particularly suited for the description of lived experience. And it has several reasons, but I think like one major reason is I think normal language is both imprecise and inflexible. It's sort of rigorous. You have to work very hard to avoid certain intuition. Mathematics doesn't have that. Mathematics is A, super flexible, and B, you can use it to precisely express what you want to say, because major reasons because we don't use it in daily life so much. So it doesn't have all these connotations. So for example, doing an epoché, doing a phenomenal bracketing, could arguably be much easier if you consider mathematical properties than if you consider like properties that have independent meaning in daily life. So my claim would be that prima facie, at least, there's good causes to think that mathematics can play a particularly wonderful role in that regard. But I feel sort of where the question comes from. I feel this thought that many of us have that isn't mathematics like very pristine, isn't it connected to machines, isn't connected to objectivity. How can this make sense of our pure lived experience? But I think the modern development in math basically took it away from that intuition. Is that a good answer or like a satisfying answer? Feel free to push back. Yeah. 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 Yeah.
but
Yeah.
another question should be whether this equals the building of computational
Do you have consciousness, you mean? Or yeah. Yeah, I think that, so I'm giving a talk. Sorry. The question is, if I understand correctly, the question is basically, if maybe I'm misunderstanding, but are you asking whether that, like a mathematical description of conscious experience, would also imply some sort of possibility of computational systems to be conscious? Is that it? Yeah.
Doing so, if it's understanding something.
Yeah. Yeah.
Is well.
Yeah. Yeah. So I think that, yeah. Yeah. What is the core of phenomenology? Yeah. 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 So I think that just because we use math, we don't immediately have implications regarding consciousness. I think the question of whether a system is conscious, if you remember the picture I just removed, where I had like sort of the actual description of the system on any level of description, computational or implementational. And then that relates to sort of a mathematical representation of phenomenology as in the form of a model or theory. This is the part that gives an answer about what can be conscious or not. Like the question, like you can describe experience consciously. You can even describe like very basic features of experience that might be necessary for experience in terms of mathematics. Did I say consciously? I meant mathematically. But then the question of whether, like which systems can exhibit an experience of that form is a question that you need a theory or model to answer. Or there are things like C-tests nowadays where you can test for conscious experiences. And that's not answered by your representation of conscious experience. I think very much in line with what you guys are doing, David and Gregoire and others. So I think that basically the whole mathematical approach to phenomenology is a way of getting a better way of grasping the explanandum of consciousness science.
Right.
And then we still have to do theories and test them, and see if they make sense and check their implications for artificial consciousness. Yeah. Go ahead.
I have a question because so we had the discussion this morning about, so I understand the fact of having a mathematical, trying to find some mathematical structures for some for describing some phenomenal experience or some concepts that appear, and it's a bit different from the way that I work now on this, where I try to just take some concepts and formalize it and then put it somewhere else to try to extend it.
Yeah.
So my question is, how would you see practically mathematizing some phenomenological experience or concepts if there isn't a consensus on the description of certain concepts in phenomenology?
Yeah.
I mean, for me, would you have a program, for example, saying that, okay, there's many ways to describe the same concept, and then we could look at a list of all the ways of doing it, and say we're going to try to mathematize this concept, capturing all these aspects. Do you have an example, for example, where this could be done?
But I think that I would not want to say this is what we need to do. I think the strong part is really that we can get around the descriptions. We can be inspired by the description, inspired by the ideas, but the mathematization itself does not rely on the descriptions. It relies on pure phenomenological data.
Yeah, but
And
I guess,
yeah.
maybe Gregoire, sorry, it's not what it meant, but that's something we reflected a lot about with Ken, what have you, a lot about, people may disagree on whether, you experience such or such, that, the structure of your experience of lived space as a perspectival manifestation or whatever, features you say are core or important in the phenomenology of consciousness. So people may disagree for variety of reasons. Some people just are bad at introspection, discipline introspection. Some people have ideological biases. Others may have different wiring of their brain, irrespective of the cause. The methodology that we have adopted to avoid infinite debates that never resolve to reach a consensus, because it's a hot topic with a lot of, I would say, conflicts or debates. is to say, okay, these are the phenomenological features that for those and those reasons we consider as key. We're not going to try to convince you necessarily everybody that they are actually right, but we're going to use a very standard token of reason in science, is that we're going to postulate that they are true. And then we're going to mathematize those features and theoretically so that helps us to understand other things that relate to consciousness. So you can, I think that the will to reach a consensus is a harder one, for having struggled for 20 years with and so we can say, okay, you know, maybe you know some people did not believe, or the results were not clear enough of some experiments. But let's postulate that the phenomenon exists as described, and now think about it. It's very important. So cut the vicious circle of perpetual debate.
So I think so there's many things to say. I'll just say two. So first of all, let many blossoms bloom. I think we have to support each other, you know, like just go. I mean, anything could lead anywhere. It's very important not just to engage in criticism. So that's the first thing. But on the other hand, one thing that I think really is really important, we have to face the fact that without a definition or methodology, or at the very least a convention of what mathematical claims about phenomenology are supposed to mean, there's no way of making good progress. We can, like, as soon as you say, you know, there's like, I'll say more about this just in a second. I'll say, actually, let's go on, and then I'll come back. If I say I come back and I forget, please remind me. But if you don't forget, So basically, okay, so let me state that again, because I'm going to remove the other part. So the question of this part of the talk, which will be long and boring, is how to do mathematical phenomenology. And I should emphasize again that this is sort of a foundation. I'll say something about this for how to do this. I'll say more about this in just a second if I don't forget. And just to emphasize again, this is like basically, or else just say this in word, this is the question, how do we represent phenomenology mathematically? And it's also the question of what does it mean to say that, you know, phenomenology has this and this structure? What do we even mean by saying that? After intuition, after analogy. And one thing I want to say is like just sort of, it's both about phenomenology, and phenomenology with a small p basically has, if you like, this is not a neat separation, but it sort of has two major areas of focus, if you like. So on the one hand, you could basically study what many people call phenomenal character. This is, I don't have a good, nice way of disambiguating these things, but roughly speaking, this is the question of the content of the experience. Content is not a good word. It's a question of what it is like to experience something in a particular fixed state or at a particular time t. So let me just add t here. So the idea would be like phenomenal character usually is conceived of like, what is the phenomenal character of me right now in this very second or in this very neural state? And then you could give an answer in terms of phenomenal properties or qualities or whatnot. So that's part of the phenomenology. But then, of course, it's also about the structure of, there's structure here too. There's relational structure, but it's more like a part of the dynamics, or actually the constitution of phenomenology. And these things are often like not studied by the same people. And the goal of this talk is really to say something that works for both of them. And the major driver for the development were phenomenal spaces, which are on this side. And as far as phenomenal spaces are concerned, we have, I think, depending on how you count, 3 other foundations you could use. None of them is none of them is viable. I can point you to papers, like they just don't work for very specific reasons I won't go into here. But the goal of this talk is to present something of how you can do both. Like you can address on the one hand this, but on the other hand also this, and go ahead. Okay. So I think we have enough blah blah. So let's give it a go. So 4.1, let's fix a little bit of notation. I should say this is all work together with Tim Ludwig, and you can read on it if you want to read. It's in the paper, What is a Mathematical Structure of Conscious Experience, which is in Synthesis of this year. So, okay, notation. Okay, first of all, let E, big E, what exactly did I have in mind? Be a set or class. I won't make a distinction here in this paper of conscious experiences. What exactly it is and what exactly you take conscious experience to mean doesn't matter because we're doing math. So in this way, mathematics is very flexible. I'm going to denote a single conscious experience just by little e in the set big E. Then we're going to need to talk about something like qualities or qualia or parts or phenomenal distinctions or locations. And so I'm going to denote this by A of E, denote and now again, you can have qualities, qualia, parts, locations, phenomenal distinctions, and there are 10 more of E. So the idea is you have one conscious experience, like for example, right now I'm having one, and then there's an input from philosophy that I'm going to take for granted, and you can choose which one you want, and then I get a set or class of qualities or qualia or parts or locations or whatnot. And I'm going to call these things aspects. And I'm going to call these aspects with a very specific understanding that the word aspect is just a placeholder for whatever you like. It doesn't matter. You can choose whatever you like. If you choose, for example, you can take phenomenal properties and talk about instantiated phenomenal properties. What you get out is a phenomenal space at the end. You can also take qualities, and then what you get out at the end is a quality space. There's a certain conceptual freedom, and I just want to do justice to that. And again, which one you choose, that's basically philosophical concept. So it depends on what you mean. Further development that we haven't written up and are not very far, you could also like make sense of this in the lab, like done in some quality spaces. Okay. And I just need a little abbreviation. So I'm going to take curly A to just denote the union over all of the experiences of this little A of E. Yeah. So it's just like all the aspects that are in all the experience. Okay. And I need one little tiny, did I forget something up here? Let's see. No. I need one tiny little sort of technical notion here, which is very sorry, it's important later for the example, but basically we'll say that this aspect A, so an aspect of a conscious experience is instantiated relative to. And sometimes I'll just leave away the word instantiate, relative to other aspects, B1 to Bm in A of E, if and only if A requires these other aspects for its instantiation. So example, an aspect could be my experience of similarity of two colors. That is an aspect of experience, but it requires the actual colors or some colors to be instantiated. You can't just experience similarity without colors, yeah? No, not the disjoint union. Yes, so basically you take this, like if they're all distinct, then you have something like the disjoint union, but I don't define it in this way. Like for example, you have green experience in many different, you have an aspect of green in many different experiences, so there's just one in this set here.
A of the object that is the point T, you have an A of E, and
Yeah.
they cannot relate between each other.
No, some thought you can. I assume you can. Yeah. So, yeah.
Because, or you assume you start from A of E inside of the set.
I think he's gonna talk about constitution.
So I think that yeah. Yeah. So I think in the purpose of like for the purpose of this question, you could think that the philosophy gives you this set, all of the aspects that could potentially be instantiated, and then you find out which one are in which experience.
Yeah, but I mean, like if you're doing something very
Yeah.
formal,
Yeah. Yeah.
assume that A of E is in the set, right?
So I'm assuming it's a set or a class right now. Yeah, we'll kind of.
It's inside of something, but you cannot use the unit.
So what I'm saying is, like, for the purpose of this question, if you want, you can think about it like this. All the little a of e, this set is given by the philosophy,
Okay.
and all the little a of e are members of that. And I didn't spend so far, neither me nor Tim thought about this very closely so far, so we'll have to do that. And I should also say that the methodology here, in this and almost all of my research, is let's make as minimal assumptions as we can. Like, I think there's lots of interesting relations to category theory at the very end, like I won't present them. But like right now, let's just do it as simple as we can, because it's going to be hard to understand anyway. Okay, cool. And now we need 1/3 part of the motivation, and that is the concept of a variation. So a variation, so let's give it the name is V, is a change, if you like, of one experience to another. To experience E prime. And you're wondering, well, aren't there like, so is anything a variation? The answer is no, specifically because experience has structure. And formally, like, because experience has structure, a variation is basically a partial mapping whose domain is A of E and whose codomain is A of E prime, where E and E prime are given as above. So that's a variation. And the fundamental idea is that, like, maybe to connect it to phenomenology right away. So for example, when you do imaginary variations, yeah, Husserl style eidetic variations, you're changing around your experience. That's like this. Or for example, if you're doing psychophysics, you're changing around the stimuli to go from one experience to another. That's that.
And the question is very important on if it's a reunion or a different set, because you're acting, basically you're doing a map on the experience.
Yeah.
You're assuming that this maps also transfer on the fibers A of AE. So the thing is that then if you assume that D moves for all each prime, you need to assume that if it's not the disjoint union, but it's a union, that it's compatible in a way, which means that if two experience changes, but they still have intersection on the median. It's supposed to be a union.
The idea is like it's a partial mapping. It means, first of all, you might no requirement as to subjectivity. So it means like you can lose some as you go from here to here. You can also get news, you don't map to.
But can't AE to AE prime be in your curly A ensemble?
They need to be. Yeah.
So, I mean,
so
the
it's
variation itself.
So the variation is
itself can be
so
become a quote unquote object of consciousness, and as such has some phenomenal character or whatever you want to call it.
we didn't think about this so far. Yeah. But the idea is, so like right now, it doesn't make sense to say V is in A right now.
Okay.
Yeah. Yeah. Yeah, go ahead. Yeah.
So rather than just the, I mean, if it was just a change one experience to another, then it would just literally be saying replace E by E prime. So really, it's more like a way of relating another thing for each aspect, or at least for some of the aspects.
Yeah.
I'm relating that aspect of the first experience to some particular aspect of the second.
Yeah, I'd have to think about this.
Just the first experience of the last, you know, how like red first relates to this other color.
So yeah, that's true. Yeah, this is basically, but this has to do with Grégoire's question also. We should talk about again later. I want to understand it in its full force. But the idea is like, if you have a variation, you can make sense of some of the aspects of the first one in terms of the aspects of the second one. Like, for example, in the case of color, change of color stimuli. Okay, cool. So that's 4.1. So now we have all the rotations. So 4.2 is just a very quick recap. It's basically just one line. So I'm going to work with just normal classical mathematics, not category theory. So for me, or for this the purpose of this paper at the present stage of the research is that a mathematical structure has the following form. So it is basically a collection of domains and a collection of either relations or functions. And I'm just going to denote them. And usually in mathematical logic, you use two symbols for relations of functions. I'm just going to use one symbol, and then only at one point will I have to say, make a distinction between the two. Yeah, this is a mathematical structure. Like, for example, in a metric space, you'd have like a domain of points, a domain of real numbers, and a metric function which relates 2 points to the real numbers. Yeah, this is just an example. Sorry, that was a bit small. Let's remove it anyway. So the idea, that's a mathematical structure. And the question we want to ask in a second is, like, what truth conditions can we propose to make sense of the statement that a mathematical structure is a structure of phenomenology or of conscious experiences? Okay, cool. Oh, S is just a symbol. This is like math BBS. It's just, oh, that's either relation or function. And I'll tell you which in the context. So these are just indices. Like usually I might have two domains, then this is just a set that has two elements. So 2 domains, J is just a set that has two. Yeah. Domains. No, sorry, this is not the same A so far. Like it's just the same symbol. It's not good. So sorry, first of all, I forgot something. Here's a J here, right? And we don't have a J there. So it's just the same symbol. Later on, we'll make the connection. But for now, this is just like if you have a metric space, let's do the example here. Right here, I'll do it in, so example, metric space. If we have a metric space is basically, so S in this case would be, you have one domain which is just the points, one domain which is just R, so this would be A1, this would be A2, and then you have a function which takes M times M to the real numbers, and this function would be, in this case, S1. So this would be a metric space. Yeah, okay, cool. And I need to say one more little thing again. So I'm just to keep things simple, I'm going to use the term relata, sort of the relata of, and now this is a mathematical structure. I'm sometimes going to denote this as structure also, but in a narrow sense of like one relation or one function. So the relata of Si are, let's make it double, it's like this. So they're basically B1 to Bm, the tuples, the M tuples in R, if S is some relation R, relation. So that's usual. And just to make our lives a little bit simpler, I'm going to say they're going to be B1 to Bm minus 1. And then the function of B1 to Bm minus 1 if S is a function. That's just a like technical thing that makes our life a little bit easier later. Okay, cool. So that's all the setup. And while we see if anyone else has questions, I'm going to clear this part of the board.
Yeah, just
You can
explain it for later.
So later I'll just give a definition where, like in basically all of the definitions, I'm going to relate to relata. And the term relata of a relation is defined exactly as here. And usually you do not speak about the relata of a function. So I'm introducing this just to make my life simpler. And the idea is it's basically the same, just that, I have the m minus 1 arguments, and then I take the function value also. And this is this is basically what the relata of a function are if you understand the function as a relation. Every function is a relation, and if you do that, you end up with this. But say again? Yeah, it's the graph, yeah. Okay, cool. So now finally, we can get to the actual subsection, 4.3. What is a mathematical? Okay. And now before I write down what I call it, I just want to emphasize this again. So there are at the very least 10 different terms that are used in the field right now, ranging from phi structure in IT 4.0, maximum conceptual structure in IT 3.x, to Q structure, Q space, whatnot. And the idea is here that we use an umbrella term And that's umbrella term is mathematical structure of conscious experience. Ah, damn it, didn't go to one line. Okay, so this is an umbrella term, and I won't write this down now, but this concerns the phenomenal character sort of way of thinking about consciousness in just the same way as the phenomenological one. The idea would be what you guys are discussing in your papers are, in our terminology, mathematical structures of conscious experience. And what I'm going to do now is I'm now going to present 4 definitions that together will give an answer to that question.
May I?
Yeah.
When you talk about this mathematical structure of conscious experience, I think I see where you're headed, but maybe not. And you associate that to phenomenal character as opposed to constitution. You are not, you therefore, maybe I reject the idea that a constitution that can be described as a mathematical structure.
No,
Okay.
on the contrary. So like when you say there's a constitution, when you use the word Hille, for example, you're using normal terms. My claim is that if we're like following some condition, here's a first proposal for that, we can actually get around using these words and just describe it in math right away, as required by computation. Okay, so here's our 4 definitions. Just bear with me. I'm going to write them down and then we can discuss them. So the first one is the following. Like, first we need 2 okay, so I'm just thinking, is it better if I give you the intuition first? Do you want to have the definition first or the intuition? Definition, great, I love it. My doctor father in mathematics always told me, like, just start with the definitions. Okay, so the first definition is a variation. And again, so variation is always V, A of E, partial mapping to A of E prime, which is here also fixing E and E prime. Now the definition is about what it means to say that it changes an aspect. Okay, that's the part that's being defined. And the aspect is in A of E. And now relative to, that's also part that it's defined, it's part of the definition. And now we have B1 to Bm being also aspects of A of E. Yeah. Now comes the actual definition, if and only if A is instantiated relative to B1 and Bm in A of E, but is not instantiated relative to and now there's a slight difference relative to V of B1. V, that's the variation of Bm in A of E prime. First definition. That is a definition that makes use of, it's a phenomenological question whether that's the case or not. Like, for example, if you vary a table by eidetic variation, as Husserl would propose, and you remove a leg, then the aspect, being a table, is changed relative to whatever it needs to be instantiated. First definition, simple as that. So the second definition is also, again, sort of a similar form.
But you could imagine, maybe it's not the right wording.
Yeah.
Kind of higher order properties, so that you look at variation of variation.
Yeah, sure.
So in that
Yeah.
case, would your definition as such hold?
Anything you can, anything that's an aspect.
If the variation itself, relate to
So-
the variations that.
So I would make a distinction between the variation and the phenomenology of the variation.
Okay.
Like,
Yeah, that's.
Yeah, yeah.
I noticed that like if the variation leaves some elements constant. So in this case, A would be instantiated conditionally to B1 or to Bn, but it would also be instantiated relative to B,
Yeah.
B1.
Then we'll just say it does not change this aspect.
But no, so instantiated is like a relation or.
Instantiated is just like word, like, so that's actually like, so Tim and I were a good team because Tim is very, very, down to earth, and I'm very, very, like, I'd like to put it abstractly. Instantiated doesn't have a meaning really. Just means that this means that A is in A of E, B1 to Bm are in A of E, and A is relative to B1 to Bm, as in the sense. Yeah.
That it's also, there's a kind of minimality, which, for example, if variation is the identity, then it's not a variation.
No, that's wrong. So I'm saying that you take a variation, and now the only thing we're defining is whether it changes an aspect relative to the B1 to the Bm or not. Either it does or it doesn't. There's just two choices. There's no claim on whether variation exists. It's just for any single variation, it's either change. You pick a variation, you pick an aspect, you pick the relative, whatever you want to call these, the BNs, and then there's a fact to the matter whether that's satisfied or not, and that matters for in a second. Maybe it'll become more clear just when I do. Let me give the second definition. And it's a similar definition, but this one targets phenomenology. Now we have a similar definition that targets math, and you'll see where we go then. So it's the same. It starts a variation V, again, A of E to A of E prime. Oops, sorry, let's do that prime. So, okay. Now we're gonna use a different term. Preserves a structure as J. So that's one of these. And now here so this is what's being defined, preserving a structure with respect to relata. That's part of the definition, and the relata are again B1 to Bm. And they're in A of E. Now comes the condition, if and only if the following is true. So now we have to make two cases. So the first case is that in the case that this is a relation, we'll just have the relation of B1 to Bm is instantiated, if you like, if and only if the relation is also, or like is true or whatever. B1 to Bm are an element of the relation, mathematically understood, if and only if V of B1 to V of Bm are an element of the relation. And this is the first case, if S gleich R, and that means a relation. So this is just saying what this definition means if S is a relation, case 1. I'll just give the exact same thing for functions. P2, we just wanted to be explicit. So if, maybe I should write this first, if S is a function, as we just had it on the other slide here, then the definition reads like follows. The variation applied to the function, applied to the B1 to Bm minus 1 is the same as, you know this, right? As the function applied to the variation of B1 to the variation of Bm minus 1. Okay, so this is just basically the exact definition of a homomorphism, just that we're a little bit careful here because we pick out the relata individually. We don't, if you were to require this for all relata, then you would basically have an homomorphism. So what did we do here? Here we talked about variations in phenomenology. Here we talk about variations in math. Yeah?
All of this makes me think, are you defining some kind of category? I'm not a specialist
Yeah,
in
not
category theory, but it looks a lot like.
not yet. Like not in this talk or not in this paper. I think that we're going there. Like, I mean, I think there's a clear way of how you could improve this definition I'm gonna present to you, which was hard. Like, I think it was probably like the hardest work I ever did in terms of like coming. I mean, and that's not like maybe it's like just shows how bad I am. But what I wanted to say is just like this definition for me was a big thing to get it, but still we have to improve it. And one way of improving is like, for example, there's an argument you could make to get rid of this input from philosophy, as do people do in psychophysics. But that's a further step, and that might lead directly to a categorical definition. But right now, everything is like pure, nice, ordinary mathematics.
That's very interesting.
Yeah, thank you. Thank you for being very nice. I'll wait for the devastating criticism. Yeah. Okay. So now we're basically, so now this is the two basic definitions. Two more ways to go. It's really like there's not much more happening now.
Spend a little bit on those two properties to make sure that we understand.
Oh, this is basically just saying it's a homomorphism. Yeah. And I'll give you the intuition once I wrote down the other two definitions. So the first one, they're like the first one, this one is quick. So this is now trying to use these. See, we have one way of making a sense between the variation and phenomenology, aspects of phenomenology, like what is a table, the essence of a table. And we have one way of making sense between a variation and math. So let's put these two things together. And basically we say an aspect A in this curly set is an Sj aspect. So I'm going to do us all a favor and remove the Sj here, because I forgot it here anyway. So this S not bold is just one of the Sj's. So an aspect is an S aspect if and only if the following condition holds. And the condition is as follows. A variation A, or any variation, a variation does not preserve A, this is the aspect, with respect to relata B1 to Bm, if and only if, you can see the rest, the variation changes the aspect A relative to B1, Bm. Yeah. So you see what we're doing here is we're now starting to make a link. So here's the aspect, pops up here, pops up here. The idea is that's starting to be the link between math and phenomenology. Like if you're you're an S aspect, that means you're an aspect in phenomenology that has something to do with a mathematical structure S, if and only if you behave under the exact same way as the mathematical structure does under variation. Now I'll give you a nice intuition just after this. I'll give you a nice intuition again where I make a picture about that just in a second. Should I repeat it anyway? Okay, so you're an S aspect. That's a part of phenomenology, like something like experienced relative similarity. So you're in part of phenomenology, but you have something mathematical about you. You're an S. S is the mathematical structure. If and only if you behave under variation, that's this part, in the exact same way that the mathematical structure does. And I'll make a picture about that in just a second. Yeah.
This doesn't use that.
Oh, here's preserves the structure. That's defined here. On the left-hand side, it says a variation does not preserve A. Oh, sorry. Oh, God. Well, that's a huge mistake. Yeah. No, it makes. Oh, sorry about that. How could that happen? Thanks for noticing this. So it does not preserve the structure with respect to the relata, if and only if it does not preserve A with respect to the relata or relative to the relata. Let me give you the picture and just. So if you do not preserve, you're changing. Yeah.
Oh, I see.
Yeah. Yeah. So let me give you the last part of the definition. Or maybe I'm thinking, no, actually, you know what? I'm going to give you the last part of the definition just in a second, but I'm actually going to draw the picture now. The intuition. So I'll keep a little bit of space here for definition 4.
Can you go back? There's a variation does not preserve S with respect.
Let me give you the intuition and then I'll explain that again. So the intuition is basically as follows. So actually, I'll put definition 4 over there. Need a little bit more space here. So what we want to do is the general idea behind mathematical phenomenology is we want to, on the one hand, we have, let's start over here. Can you see that? So we have basically phenomenology. And I'm just going to draw the very same picture again I drew in the beginning. So this is the desk where by now David is still trying to keep up, but Sean is really banging his head on the table because he thinks it's so stupid. They should have done it in category theory. So here's phenomenology, right? And over here is mathematics understood as a language. So mathematical language. Language, yeah. So like, let me just give you like maybe, you know, like I'm just drawing some pictures that make you think about math. And what else? Like maybe, you know, like projective geometry, mathematical language and phenomenology. And what we want to do is we want to understand how we can use this to talk about this. That's the goal. And what we're doing here is we're making use of one fact that exists already, and that's what philosophy gives us. There is, I would call this a baseline correspondence, basically. There is already a relation, and the relation is there's a set, that's exactly the curly A of aspects, meaning a set of qualities or qualia or phenomenal distinctions or whatever you want. So this is there because of philosophy. We can make sense of parts of a phenomenology, like parts of phenomenology in terms of sets. And what we're doing now is very simple. We're now saying, well, how can we get from the set to the actual mathematical structure? Well, it works like this. So on this side here, let me just use one dot. That's a whole mathematical structure. That could be like a metric space. And over here, somehow, or to be more precise, it's the metric of a metric space. Yeah, it's the D. It's one of the S's. Let me just write that here. That's the little Sj maybe. And over here, we pick like an aspect of phenomenology. Like this could be like this little A we had. Yeah. Now the fundamental idea is just we now have to say we have to give conditions under which an aspect has something to do with phenomenology. And the condition is very simply, well, you can vary this, and the variation of experience because of this baseline correspondence is always a variation of the underlying set. So you vary this in some directions and it's being preserved, right? So this is preserved. And whenever the structure is being preserved, the corresponding very same variation on the phenomenal aspect should not change. So I should copy this identically, yeah? So it's not changing, not changed. Sorry, I'm writing this here. Not changed. That means that the aspect behaves exactly the same way as the mathematical structure does in the variation. But then also in other cases, it's being not preserved. So I'm going to draw little red arrows and cross them out. Yeah, so these are cases where it's not preserved. And in these cases here, the same should happen, but the corresponding aspect should not be, should be changed, which basically means it should go away. And no, like it would be just, these are supposed to be equivalent in the sense of conditions. Like what I'm saying, a variation that preserves here should not change here. A variation that doesn't preserve should change. And that is the definition between this concept here of an S aspect. If you do that, you're an S aspect. You're basically something in phenomenology that behaves exactly as the S does here. And let me just give you the last part of the definition, and then we can really make a big, that's all I wanted to say. There's one tiny little point, but I'll keep that, and then we'll look at an example to make that very clear. And I picked out a very nice example, I think. So that last bit of the definition is basically now the big answer to this. What is a mathematical structure of conscious experience? And this is the final answer we can now give. A mathematical structure of conscious experience abbreviation MSC. So a mathematical structure of conscious experience is now the following. And I'm going to use some mathematical structure. Okay, damn it. Gonna have to write it out. A mathematical structure. And now I do my bold-faced S. That's the mathematical structure. Is A, and now comes the abbreviation, mathematical structure of conscious experience. So that's a condition for a mathematical structure to be a structure of conscious experience. Now here come the two conditions. If and only if the following two conditions hold. And now is basically the upshot of it all. And I should say that's a generalization of all of the methodology we had before, trying to resolve some of these things. So let's continue here. The conditions are as follows. So the first condition, I'm just going to call it S1, is the domains AJ, they were domains of the mathematical structure of S, are subsets of this curly A, which is just a set of all aspects that we have. That's a condition we had used before, like in phenomenal spaces. And the second is for every Sj. So this is like the actual structure on the mathematical structure. There is an Sj, aspect in A. Yeah? And that's it. Yeah, these are the two conditions.
So the main,
Yeah.
what's going to differentiate this statement from a statement that is generally true in science, for instance, take the phenomenology of the orbit of planets around the star, you can observe with a telescope,
Yeah.
And then you have a mathematical structure that will describe, the dynamics, and you could perfectly trace that this way. You have to have this kind of if and only if basically domains that describe the orbits are a subset of all possible orbits. I don't know.
Yeah.
And for every structure, mathematical structure that describes the physics of orbits, there is a S aspect in A. That means like the way you would observe it in your telescope, for instance. So here it's because sorry if the formulation is not quite right, but you get the intuition. But so here, what is going to distinguish your statement from this more general statement is A, derived specifically from the phenomenology of conscious experience.
So I would
and
put
not from a telescope or a recording device.
Yeah, so I would put it a bit differently. So in general, generally speaking, there's a problem called the Newman problem. Did anyone hear about that? Like the so-called Newman problem. Whenever you want to make structural claims about reality, and it doesn't matter whether that's phenomenology or physical, there's a certain problem that is very pervasive, and that basically means so I could tell about, I could explain it, but it would take a bit. But it basically means that the usual way of understanding structural claims about reality on their own is completely flawed. And the problem has been known for about 100 years. And there's a larger number of possible solutions, and all are very technical, and you have to change subtle things. This one, I wrote a paper about this. You can, if anyone's interested. So this way, which really came out of consciousness science, is a way of reformulating the truth conditions for structural claims in such a way that the Newman problem does not appear. So let me try to say what this means for phenomenology. Basically, this condition is not, there are problems with all previous conditions, which you can read up, which on my mind show very clearly that you cannot work with the previous conditions in terms of foundation. Still, you could say, well, I'm just going to drop this, and I'm just going to say that, the SJ should be a structure of conscious experience, and I'll try to make sense of this without this S aspect part. And what you can show then is that this statement is void over and above a statement about the cardinality of these AJs. So in other words, sort of, you cannot, like structure on its own cannot fix structure if you don't sort of take care of it in such a way, if there's no condition that relates the structural claim to the actual phenomenology. Not sure if that makes sense. Yeah. Yeah, so
I get some sense of it.
yeah, so basically, so I mean, yeah, so yeah. Are there any yeah. The Newman problem? Okay, so I didn't prepare that. So fundamentally, the Newman problem is a statement like this. The structure, so you have the structure of the world is S. That's the way I think Newman framed it. That's usually it's only discussed in the context of epistemic or ontic structural realism. But it's very important also for all theories where you don't by hand say which structure it targets. Like a theory, we want when we do mathematical phenomenology, we want mathematical claims to fix phenomenology independently of the fact that we are going to have to say, well, the metric function is about relative similarity. We want to sort of get rid of this dependence of language. And this is structurally the exact same thing. We are in an epistemic structural realist context, and we want to say something like the structure of the world is S. Now, the way these claims are usually understood, and usually, I mean, the last 100 years is as one, you basically say that same thing, AJ are properties of the world, right? The HA are again the domains. And the second thing that you say is then the SJ exists. And the SJ exists literally just means that you can endow these properties. Like, for example, let's take a relation, I'll add a 2, it's a binary relation, exists, and that literally means that you can take these properties and define over these properties a relation as is specified in here. This is the normal, the explicit way of understanding structural claims in the last 100 years. And the Newman problem appears because you can always define such a relation. It's void to claim that these properties are like that you can define a relation over these properties if nothing fixes the relation. And there's a number of solutions for this problem, but this here, and that's the content of this paper which I wrote, is to assert that this is another possible solution to this problem.
But you cannot need the proposition to define the relation.
Problem is basically, what does it mean to say that S2 exists, that the binary relation exists? What does it mean? Yeah, so usually it means that you can take the properties and then you define the tuples over them that are the relation. And
the other direction from relations finding propositions.
so I don't get the question. Yeah. What was the question? Yeah.
The fact that you start from R exists and then get propositions. I don't understand.
The problem is that there's a natural way of reading this part. And the natural way of reading this part is just not very good. It's just like it's borderline meaningless. Like there's a literal theorem where you can show that you can literally show as a theorem that any such claim is true as soon as the cardinality of the domains matches. If the world has at least the cardinality of the domain, statements like this are true. And you can even reformulate it in Ramsey sentences if anyone worked with them. Like Ramsey sentences are basically is one sentence that summarizes the content of a whole theory in some sense. So the problem is there's a fundamental issue with structural claims whenever they're supposed to stand on their own. And that's an exact issue we inherit if we do mathematical phenomenology. And one way, there's various ways of resolving this. I can point you guys to a good paper that reviews them. But one way of resolving this directly is just by saying, well, let's use slightly different truth conditions. Yeah, so this is like we take basically changing the truth conditions for these claims is like saying these things now mean something slightly different. And we replace this by the newest two, which is basically also requiring the existence that's implicit, but in addition, it's also requiring that there is something in the world that behaves like the structure does under, roughly speaking, automorphisms. This is the new requirement. Yeah. That's exactly the problem. Yeah.
So it's saying it needs to be more subtle because
yeah.
I don't understand why you want. I can understand why you want
Yeah.
to use force. I don't want to understand like why practice. You change R, for example, to account for things that can be R depending on context or R depending on.
Oh, you don't change R.
I mean, like you're
Yeah.
saying that it's not R strictly relation between two propositions.
No, it is. So R is still here. I'm talking about properties, but R is still the very same thing. It has been from the start. The condition for making a claim about the world, that the structure of the world is R, has now changed. Whereas here we just, so in a sense, if you think in terms of first order and higher order properties, this here just requires the existence of first order properties, and the rest is math. You can't just define it. The new condition requires the existence of first order properties and higher order properties. Like, for example, a simpler version of this, which doesn't work, is you could say, well, what if we don't just require that R exists, but if R has, RT, like binary relation 2, we could say, well, if R has RTN, we want there to be an N order, like a property, a higher order property, which has N, like RTN as well. The philosophers called audacity, I think, adicity. So like you could make other things, but they won't work. You need this. Yeah. Yeah.
What is captured by this? So for example, if you take a set and you say, I want to give me the sphere, right?
The sphere?
The sphere.
Yeah. Yeah.
To give me the sphere doesn't make sense. You're gonna give me a sphere, and depending on what you mean by sphere, like is it topological, is it developmental? But I can always talk about properties of the sphere, like variance or. So it means that if you want to talk about the sphere, you take a way of it. Take one sphere and the property depend on the way you're going to talk about it.
Absolutely.
Then it doesn't make sense.
Perfect.
To this kind of.
Well, it has to do with that. So basically, if you have two mathematical structures that are equivalent, for example, you can have a topology, you can define a topology based on open set or closed sets. Only one of them will be able to satisfy this. Like this thing breaks equivalence, mathematical equivalence, because the exact requirement of like this definition is that everything that you explicitly list as part of your structure needs to have something that corresponds to the structure in phenomenology. And just to say, this works perfectly for many of the simple examples you have in mind. And just to say, we'll continue the discussion, but what I wanted to say is like the example I wanted to show you guys is not the very simple one of like relative similarity, which is just basically too simple. But for example, you can take this concept of phenomenal unity, which is in IIT and all other theories, and you can ask, okay, so what is the mathematical structure that describes phenomenal unity? And you can go through these things and you can find it.
Can you show us?
Yeah, this was what I wanted to do. So let me just. Hello. Oh no, one of them is Grégoire. And one of them is Niels.
And Ken has a breakdown of his network.
And one of them is
Christophe is best. Okay, so we had an issue of connection. Let me see if the
the YouTube thing is still working. Oh God.
yeah, But it's working, but it's for now it's frozen.
Oh yeah. Maybe you have to start the other one.
YouTube thing is frozen. YouTube thing is frozen. Do I need to read? No, it's back again.
Okay,
Oh,
good. Are we?
Just start again.
yeah, it's
Okay.
frozen again.
Can I go? I think it was like here. Can I go?
For some reason it's frozen, but it's okay. I'll save the video for later. But the Zoom is working, so you can.
Is it still? But maybe you need to start the recording or something. I can.
It tells
This
me
one.
that,
Yeah, it's. I think it stopped.
live
Just.
stream is on.
Oh, it's still on. Okay. Well, anyway.
For watching now. Jesus Christ. Maybe I should. I'm gonna start it again. Should I suggest that I? Oh, wait, something is happening.
Yeah, I think I'll catch up.
Oh,
If you start it again, we'll have 2 videos.
why is he tumbling on YouTube?
What am I doing?
Not tumbling. Yeah, appears on YouTube.
Hello, I'm the talk.
Instead of you. So now let me do something. Okay, no, I think it was my computer. So all of that is my fault. Okay, so we
We're
can
good?
continue.
Yeah, okay.
All right.
Wonderful.
We
Yeah,
have
so
Lenore now who's here.
oh, Lenore's here. Hi, Lenore. So basically the question that I just wanted to answer at the very end is why is this about phenomenology? And that has to do with the question what variations are. And basically there's 2 ways you could interpret variations, yeah. So on the one hand, you could really just, I kind of said this before, but variations could really just be induced, if you like, by stimuli. Yeah, and in this case, what you would do if you consider variation that are induced by stimuli, that would literally be psychophysics. But on the other hand, and that's the reason why it really ties into phenomenology proper, variations can also be eidetic variations. So variations as imagined variations. And, hypothetically, at least, that's the methodology by which you make progress when it comes to Husserl. So this is very much related to phenomenology with a large P. And the big hope that Tim and I had when we did this was really that this sort of formal stuff can not only help us avoid the constraints of normal language, but also maybe ultimately get us to a place where we can actually unify approaches, because there's many things you cannot find out. Very detailed knowledge about color perception is just not accessible to introspection. We need psychophysics. But then again, many structural facts about the constitution of phenomenology are not accessible to psychophysics. So we need eidetic variation. And that is the big hope. And that is specifically also the big hope in relation to the proceeding right now. People on this end, like David Rosenthal, whom I very much appreciate, but they were like, oh, introspection is just shit, it can't be precise. And people on this end were saying, well, here you can never get to the ground truth. So maybe we can unify it. And then do all the stuff with the models I explained at the beginning. Okay, so let's so Gregor, I think you suggested that we take a break and we can actually, before we go into the example.
Right, I think you wanted to continue asking.
Or asking questions. I think we should do that. And I will also
No,
question.
Kenneth and
Yeah.
other group that are
Yeah.
online. Oh, so you have to.
Yeah, comments are great. It's shit. I knew it. No, just kidding. Yeah. Yeah. Okay. Yeah.
And it was also a good answer for
Oh, okay. Yeah, thank you. Yeah.
And I got this feeling that your solution comes to me as like a phenomenological approach, but taking it back to the Kantian point to some extent. And it's a very clever way of dealing with it, I think. And like what you just said, your hope, and I think it's quite useful. And
Yeah.
because that's what I thought too, like, following
Yeah.
the-
Yeah.
That was exactly what I was
That-
thinking. That could be maybe something
Yeah.
to. This could, provide more, like a better intuition to phenomenology as well, like a better language.
Yeah.
Can you repeat?
So the answer, the comment was that it's not totally shit. No, I don't. No, just kidding. No, so yeah, that's very kind of you to say. Thank you very much. I mean, so I should emphasize, I think really this is just like a first step. I mean, the thing that I ultimately really care about is that we need to have conditions for what renders statements about the mathematical structure of phenomenology or conscious experience true. And yeah, and you have to understand, yeah. And so, yeah, and I think that's sort of what, but it has to be improved. Maybe we can have better other ways, but this is like a first step, yeah.
What I seem to have heard, but I was coming a bit with the camera and
Yeah.
everything, is that maybe this approach is also relevant, or there may be some, more generally speaking, usefulness of such an approach to guide or structure phenomenological investigation.
And I think that's very much.
Okay.
Not really, no, please explain, yeah.
Could be useful, like, I can't really explain now, it's gonna be a whole.
Kantian what?
Sentiment technique.
Oh, yeah, that's Johannes.
And
What is
What, German?
I know a little bit, I mean, but not very much. Just the yeah, I mean, just the part of just the first half of the Critic of Pure Reason we read in elementary school. Just kidding. Yeah. No, I was sick in elementary school when we did that. Yeah.
not that it's gonna be the answer.
Yeah. But what is the relation? Could you explain a little bit?
The solution is, instead of, like, it's to explain a very, very, very brief thing. If you know anything about, critique,
Yeah.
so, like, basically you've heard of this, like, finlandization,
Yeah, sure, yeah.
That's something that's.
Yeah.
So instead of that,
Yeah.
Something that's, not something that.
Yeah.
Start, that's what we go to.
Yeah.
So instead of that, because we can't really know, so, that's where these all this phenomenon or phenomena come into, the play picture. And we want to deal with that.
Yeah.
And that's
Yeah.
also wanted to do as well, but in that necessary, like, still in content.
Yeah, I see. Yeah.
But, to, like, understanding, like, that it's a very, like, complicated structure that, Kant was trying to build, like, the architecture itself is very complicated, but that's why maybe it would be helpful for you to develop.
Yeah, it would be. Yeah.
Like, the very, solution that.
Yeah, no, that's a super interesting perspective. So I'll probably ask you again about it later.
Yeah,
Or, yeah.
but I wonder if Leonard, would you like to speak? Because I see that you turn, your mic is on, or do you have a question at this point?
No.
No? Okay. We can.
Hey, hi, Johannes. No, I
Hey,
don't wanna say
Lenore.
that.
Thanks for joining.
Well, I was watching on YouTube, but that went off, so I came
I
to,
see. Oh,
yeah,
yeah.
here, but, I'm gonna be leaving a little bit, but
Yeah.
it's been great. You're
Thank you very
fantastic
much.
talk, really
Thank you.
fantastic.
Thank you. Yeah, very
Fantastic.
kind.
It's because I put my foot on the cable, on the network cable, and and it disconnected. Sorry about that, but it's reconnected now. Thanks to, good to see you, Leonard. So I guess this is somewhat, I mean, I think it's an important point, and unfortunately, Ken has some struggle with network, so he had to leave. But with respect to your framework, it just hearing that question about, the category, the transcendental category of experience, somewhat in Kant. There might be structure, mathematical
Interesting,
structure
yeah.
that are actually the right, quote unquote,
Yeah.
The true, quote unquote, structure to explain the phenomenological set, but that are not in any way, part of those structure are not in any ways appearing in the
Yeah.
phenomenological set, like it
Yeah.
doesn't have
Yeah.
phenomenological character. So, in other words, there is some aspect of maybe the mathematical structure that could underpin phenomenal experience and be constitutive of them, and you would need to invoke such structure to account for them, but that would not be in the set of the properties. So they that you are describing. So I wonder how,
Yeah.
with your sort of, I know it's not an
Yeah.
isomorphism, but in the example
Yeah.
that you gave,
Yeah.
how can you account for that? Basically, the structure of consciousness in terms of the constitution and
Yeah.
shape it
Yeah.
is broader,
Yeah.
quote unquote, than its
Yeah.
phenomenology.
Yeah. So I'm gonna give you
But
some.
contains it
Yeah.
as all
Yeah.
the variations you want
Yeah.
at the level of a subset, but
Yeah.
it's
Some.
the phenomenology is incomplete.
Yeah.
Basically.
Yeah. So I'm gonna like I can only give an answer which will basically probably Kant will turn around in his grave. But like from a more physicsy perspective, the idea would be like you could still make the distinction between like epistemic states of structure and ontic states of structure, where ontic is not supposed to mean the thing on sich, but it's supposed to mean like I could now, like for example, if I came up with a theory of consciousness that, as I said, I mean, so it'll have to relate to the phenomenal structure in some sense. Well, it could be that the structure the theory actually models is much more pure and pristine and good and clean and has additional stuff. But what counts is not like what exactly it postulates. What counts is can it explain that which we find. So this is very operationally just what
So
we
it's not a
find.
requirement of your,
Yeah.
what I call
So-
isomorphism is not a requirement.
Yeah, it's in the very same sense, like if you do general relativity, you find out that, like this part of the universe has, like positive curvature and, like these and these properties. And then we need to theory, a cosmological theory that accounts for the part we know. And it can do in various different ways. It could be like the Friedman, whatever, Robertson-Friedman model does it like everything is like we are seeing it here. But then there's other models where we live like in a special bubble of in terms of the shape of the universe. Yeah. Was that sorry to be physicist here.
I don't think, I was
Yeah,
wondering whether
yeah,
that was
yeah,
kind of somewhat
yeah.
in conflict
Yeah,
with this approach, but based on what
Yeah,
I get in
yeah.
response, I don't think so.
yeah.
But of course, yeah.
Yeah.
To protest,
I- Yeah, I think that in a sense, like ultimately, like what happens in physics is that the actual question the question of representation is super important. If you do cosmology, which is the science of like the large scale structure of the universe, it's the question of what the structure is, like how space is curved and how to find it out is like one of the key questions you have to ask. So it's not that we don't care about this, but in a sense, as far as theory development is concerned, we have another resource that we don't have so far in consciousness, and we probably don't have for a very long time, namely two resources, actually. On the one hand, like when you build a new, let's say, unified physical theory, you can basically make sure that as long as you link to the structure of the theories we thought were correct before, you're fine, right? You don't have to think about like, what would it mean? But you're just saying, well, here's a limit and there's a structure we know. So that's the first resource. And then the second one is even more important. In physics, we're in a process of theory building where small changes to the structure, like let's say you add the clock effect to general relativity, will have empirical consequences and you can maybe rule it out. And so in consciousness science, we're just not at that point. So we have to start somewhere. Ultimately, maybe we understood the conditions of how the structure the theory accounts for relates to the structure we find. Like, for example, like maybe the theory does have projective geometry in a precise sense, yet, like in practice, there's like small deviations because which come from our limited resources, both in introspection and in the lab.
Right.
Yeah, exactly. So stuff like that. Yeah. Yes, the gentleman in the back, please.
The first one is why do you consider B1 to Bm to be in the same space than A, and why don't you consider simply functions from AE to something, so that when you say a variation preserves, changes an aspect of A relative to the function, it means that it doesn't factor by the function, basically. Like it means that if you apply F on V of A, it's not F of A.
Mhm.
So because my point is the B1 of the Bm
Mhm.
could be, if I see them at, for me, I think about then like descriptors or something that say something about A. They live in the same space of A, and so it's a bit strange that the variation. I mean, like it means it's a bit restricted to see. It could be restricted to have that the variation applies on A the same way it applies on B.
Yeah. Yeah. So first of all, I think that could be like a first avenue for improving. Second of all, I didn't get exactly from where would the function to where would it go?
Instead of having B with
Yeah.
EN,
Yeah.
you can put like A.
Yeah.
You have something that's
Yeah.
like A2 something.
Yeah.
Or
Yeah.
something associated to A2 something.
Yeah.
Like for each A,
Yeah.
so
Yeah.
you-
Yeah.
okay.
Yeah.
I mean, like, and this is
Yeah.
and because I understand now also the thing that you asked that it is aspects, basically the S aspects are all the structure that preserves that preserves like the things like in this setting the S structure would be basically what doesn't change like all the things all the other functions that you can build on A or the set
Yeah.
on A
Yeah.
that under
Yeah.
variation do not
Yeah.
change with respect to B.
Yeah.
And so then
Yeah.
you can
Yeah.
make it as
Yeah.
factors
Yeah.
two.
Yeah, you could basically take this relative to idea and like introduce a tiny little bit of formalism to take care of that. That's true. I do think that sort of it makes sense that they're in the same, like, so the idea is like relative similarity of colors, or let's just say similarity. You have two color chips in your experience right now, and then relative to these two color chips, you experience them as similar to each other. That's not really true, but like phonologically speaking, but or like you have one color chip and you have another one which you engage your memory. So in a certain sense, you can therefore you have a memory on the one hand and the color chip, and now you experience them to be similar or not. So in a sense, the S aspect is that the similarity that's later being modeled by a mathematical structure. So the idea is that in this framework, at least, like for a similarity experience to arise, the things that it's relative to are in the same experience. But I fully agree with you, like we just kept things as simple as we could.
No,
Yeah.
probably it's possible even that
Yeah.
both are but like if I think for me the way when I see it I try to think about causal relations or something a dependency and what can happen is that the dependency is on things on which B will not act naturally or and this but
yeah
I mean it's not it's just a mark
no it's good and
and the second thing I think so I was thinking with your drawing which I find very good because I understand. I mean, it allows for me to get a very concrete idea.
Mm-hmm.
So I think it makes me think about René Thom's approach to phenomenology, which is basically you have the dynamics and the attractors of
nice.
The shape. So, but so something that can happen, I think, is that something that exists, so an aspect becomes nothing and not becomes an aspect.
Yeah, but this is the reason why we model it with partial variations here. You can literally, the aspect can be gone. Yeah.
Okay.
Yeah.
So this you say you can get through partial maps.
That's the way we modeled it. I'm not 100% convinced is wrong, like I wouldn't put it out, but I'm like eventually like it doesn't feel to me to be the very best way of modeling it. Like, yeah. I think that ultimately, like, so the concrete project we talked about a little bit, but it's at the very early stages is like one thing you don't find in psychophysics is this dependence on philosophical quantities. Nobody in psychophysics is like, okay, so look, what are the qualia and which are there? What are the qualities? So they do that in the lab too. Like if anyone knows color spaces, the actual, what they call the quality is also part of the methodology you apply, you get it. And so based on this idea, you can reformulate this whole thing much more abstractly, where you also ultimately get the aspects. And that's the process we're doing. And it feels to me that this is converging to a way of formulating it, which is basically very close to a categorical variation of a formulation, where basically you don't need all this tiny little nitty-gritty mathy stuff here, but you basically consider the category of the structure you're interested in on the one hand, and then you consider the category of variations in a certain sense of experiences. If they match up, you're fine.
The vanishing part is something that I think it's something very very
important,
very particular thing model, like,
Yeah.
so you mean that the partial map, basically, you interpret it as a way saying that the aspect has no represented once I
Yeah.
do a variation.
If it's
so
not-
it's the
yeah.
same thing that making it disappear.
Yeah. So the
That's not
idea,
how-
yeah.
Okay.
Yeah, so the idea is like if you're not in the domain, so partial mapping means normal function domain is the whole domain.
Yeah.
Yeah. So if you're not in the domain of the partial function, then that means you're disappearing in the change. Yeah. But yeah.
Because you can also imagine like thinking about the partial map as saying there are some things on which my variation doesn't act.
Yeah.
And they don't have represented.
Yeah.
Because we look at what is changed.
Yeah.
But
Yeah.
it's true that it can also
Yeah.
you can apply to
Yeah.
say that it
Yeah.
changes to nothing.
Yeah. Yeah.
Like it,
Yeah.
Which is just still a change.
Yeah.
It's-
Yeah.
But yeah. Okay, cool.
Yeah.
Thanks.
Cool. So yeah, so I mean it's been 2 hours. So what I was planning to do is there's basically two good examples on my view which can sort of illustrate. Yeah, so one of them I don't think is very suitable for this audience, first of all, because it's about psychophysics. Second, it's because you have to yeah, let's do the other one. I didn't prepare the first one. I'd have to be. Yeah, okay, okay. Yeah.
Personally, I would
Yeah.
enjoy it because I
Yeah.
think I have some
Yeah.
draft.
So-
but if you don't feel like it, don't follow.
I mean, I didn't plan for it. I'd probably have
Okay,
to
so
improvise a
then
little
do-
bit. But so the one I wanted to present is the one which I think it's kind of counterintuitive a little bit. And that's why I like, and I think it's much more about phenomenology in the sense I wrote down. It's not about, what is the relation between colors and what is the mathematical structure, but it's more about something that goes beyond just simple things accessible to psychophysics. And the result is also very fun. In a way, it's very funny and kind of a little bit strange, but at least to my mind. So maybe let's do this. Yeah, and I'll try to make it not too long. Okay, so, and this example is basically unity of experience. So who knows what the unity of experience is? Whoa, that's a lot, yeah. So I think that,
Synchronic, diachronic, both of them.
yeah. So I mean the synchronic, that's for sure. But so my feeling is that in most cases in the actual literature, like it's just dropped as something that makes sense. Sometimes it just means it's about the fact that somehow you have every system has one conscious experience. But there's actually a lot of very good philosophy about what that is. And what I want to work with here is a paper from Bain and Chalmers in 2006. Tim Bain and sorry, 2002. And what they did is basically they asked the question, what could we take phenomenal unity to mean? Yeah, and so here's they have a bunch of theses, and I think that's the one. That's the one they like most. It's called subsumptive unity thesis. And thesis means it's a thesis that can be true or false, but it's also a way of saying what it means for something to be unified. And I'll write it down here. So I'm going to abbreviate this as SUT, something like an SUV, but just subsumptive. Yeah, you'll see why in a second. Yeah. So subsumptive unity thesis like an SUT, and it reads as follows. So maybe I'll stick with white for now. So I'm going to write it down in their terminology, and then I'm going to translate it to aspects just in a second. So they use the terminology of phenomenal states, if anyone knows that. It's a little bit technical. So for any set of phenomenal states, phenomenal states of a subject at a time, the subject has a phenomenal state. The additional one, subject has a phenomenal state. And now here comes, and that additional phenomenal state subsumes each of the states in the sets. So let me make this more accessible and also And like A, let's relate it to the terminology we had here, and B, let's make it more accessible. What does this mean? Why do we come to think about something like this? So here's how it works. So I'll write it down in yellow. So what that basically means, like in the terminology that we've applied, so let's give an if here. So it means that for any set X in one of these A of E's, which is the aspects of one experience, there is an additional aspect and I'm gonna call it AX. It's also in A of E, and it has the following aspect, namely, the aspect says, so this is like saying what AX is. In like language sucks, we know that, so apologies for that. What it is like to experience the aspects in X as part of one experience together. Getting a bit tired. So the experience is E together. So this is basically what they're saying, yeah? So again, this aspect is just going to be called A of X, yeah? It's an additional aspect. And so just as a side note, I'll do this here. This is AX is relative to X. So, or I should say, relative to all A in X, yeah? So this is just, this means like, this is this notion I had introduced before, which we need for the definitions to work. Okay, and now here's the claim that I want to present. So this is like this is, I think, a true phenomenological observation. It is what it means to say that consciousness is unified according to this thesis, which, if I understood the paper correctly, is like the thesis that they think is best, and it also struck me as the best thesis of understanding phenomenal unity. That's what it means. And now here's my claim to apply all of this. Are there any questions up to this point?
I mean, to me, it's a very classical
Yeah.
question about consciousness that has yielded over hundreds of years now paradoxes that are very fascinating, and problems of representation of that unity. For instance, can the set of all experiences belong to itself?
Yeah, stuff like this, yeah.
Kenneth Wilford have been exploring, how you can have consciousness can be conscious of itself in the sense of pre-reflective self-consciousness, and try to look into non-well-founded set theory to kind of get at this sort of mereological sure. Paradoxes. Again, here you're gonna apply that sort of problem to
I think that, so I just want to say that if this is an phenomenological observation, which I think it is, like, then here's how the math. Yeah, sure. No, the paradoxes, I agree, but I'm not going to talk about them. Sorry about that. But so the claim is really just, the claim is basically just like AX is an X aspect. What is that supposed to mean? Well, X is a subset of A of E, right? So you can, that's a unary relation. Yeah, and previously we had S aspects. So now we're just saying, well, S is X, right? So previously, sorry, that was a bit quick. So we have X from over here, right? So we have X over here. X is a subset of A of E. Therefore, it's also a subset of curly A. Therefore, it's a unary relation over curly A. A unary relation is a relation with just one argument. And all of the points in it realize it. So that's a mathematical structure. And the claim is, we'll just have, it is a structure, and the claim is AX is an X aspect. And so this is something we can now prove based on the formalism. Before we do the proof is, what does this actually show you? The proof is not so simple even for these cases. Well, basically, what you can show if that claim is true, let's just do this in here before we look at the proof. So what you can see is basically is that if you choose curly A as the domain of a structure, and you choose a particular collection of subsets where tau consists of sets x1, xn, or actually I should write it differently. Tau consists of all x such that the subsumptive unity thesis is true for x, which for various reasons, including the ones that you just mentioned, can't be any. Otherwise you have so for most or some, or for, yeah. No, if it's any, it can't work. You have an infinite regress then, because you can always take this.
You can use non-well-founded set.
Well, I don't know that, so yeah.
I mean, it's
But
this is
maybe any,
just
okay,
what Barrel
yeah.
was saying, the circularity, we shouldn't neglect it.
I don't think, yeah.
Phenomenology.
This is exactly what I want to discuss once we're done with this example.
Okay.
And I think that they're very, yeah.
Well, I mean, when you look at that, it looks like you're just saying that AE is a like complete lattice or something. So there wouldn't be any paradox. You can have
So
you have a lattice and you say subsume is the partial order, right? And you're saying
so A is,
any set has an upper bound.
so if I formulate it for any, I can always take take the whole space, and then I need to get another aspect for the whole space, and then I can take the whole space plus that another.
So,
This is
okay,
like,
so
yeah,
subsume needs to be strict. So,
yeah.
yeah,
Subsume needs to be strict. Yeah.
But you can't
Yeah.
have it.
So anyway, at least I'd say it like this. There's lots of literature, like Vanya has written on this as well, for those who know Vanya, like about how this leads like to infinite regress. For me, I'll do a simple solution here. It's just an example. I just say, well, it's probably not just any, but most or something.
Let's accept this.
Yeah, but- yeah.
Well, you need that strict, though, right? Wouldn't it make sense just to be a complete lattice, and at the top is just like the whole experience itself?
But if that's true for any set, then you can take the whole experience, and then you still need get another one in
But
addition.
I'm saying if subsume means less than or equal.
Oh, that's what you mean. Yeah, maybe that. Yeah,
Isn't that like?
Yeah. could be. But here, like, yeah, maybe. Who knows? Yeah.
But
Yeah. Maybe. Yeah. So anyway, I'll just do the simple one. So the idea is literally that this is a MCS, mathematical structure of consciousness. Like maybe it's all of them, maybe not. But the point is like, so we take as the domain, this is like this domain here. And this is like an abbreviation for having this structure. And why is it a mathematical structure of consciousness? Well, we have these two conditions. The first is the domain is supposed to be aspects. We get that for free because we choose A as the aspect. And then every single one of these structures is an X aspect. So yeah, and so that's very interesting because now you can, so there's where math stops and intuition starts. You can, for example, look at vision and you can say, like, at least you can give so vision. No, visionary consciousness, that's not a very good word. I'll use it anyway. You know what I mean, like visual consciousness. So you can take a look at vision and you can at least think, so which of these are arguably experienced as unified in that sense? And then maybe, like at least we give arguments in the paper, you can say, well, maybe tau actually satisfies the axioms of a topology. And this say, in this case, like, with closed sets. Yeah, so this yellow part here is a little bit hand wavy, but the funny thing is that somehow unity, phenomenal unity, has something to do with something like topology. And I find that super surprising or super interesting because unity is supposed to be like this super remote kind of mysterious thing, but well, mathematical structure, if you just go through with it, very like down to earth, well, it has something to do with topology. And well, because of this. Oh, you mean you want an intuition or an answer? Well, the intuition is yeah. So this has nothing to do with it. So the fact that phenomenal unity is related to locality is an additional fact that you can now investigate. It's not the reason that this holds true. The reason that holds true is basically because every set satisfies the definition of an X aspect for
But at each time you're not talking about the same thing. Like,
yeah, maybe a hierarchy.
A
Yeah,
of
yeah.
X is not X, so it's you're pointing at X, and then you get a lot of A of X pointing these things. And when the topology is telling
Yeah.
you what it is,
Yeah.
actually, it's telling you what is basically how things are close to each other.
Yeah.
And
Yeah.
infinitesimal
Thank
manner.
you. Yeah, thank you for being here.
So that's why I
Yeah.
don't understand the relation with the topology. So you cannot
So,
make it.
so all I'm saying, yeah, sorry, go ahead.
What kind of maybe
It's quite close to the lattice view.
Yeah.
Yeah, exactly.
So I'm-
Because
yeah.
Closed set
Yeah.
topology
Yeah.
would be the complete lattice.
Yeah, exactly. Yeah.
Basically, you're saying if you, instead of taking the whole thing, what we were saying, take just these X that you're
Yeah.
allowing.
Yeah.
These do form a complete lattice. But
Yeah.
the topology is like a couple of abstractions.
Yeah. Yeah.
You find
Yeah. Yeah. I like that too. But what I want to say is like that is something as, yeah, sorry, go ahead.
But that topology or the topology of the lattice. Because you're looking at
The closed sets are form a lattice themselves. So, if you take any.
close sets on what? No, but the topology will be on what? Is it the lattice that defines the
sorry,
topology
yeah.
or the topology?
Sorry, I don't really mean topology. I guess I mean I think it's a frame. It's normally called. It's like the axioms, the order relations, the whole
Okay, I
order closed
understand.
set.
Yeah, okay.
Yeah. So, yeah, so I'm totally open to the fact that this example can be improved. What I like about the example is that it relates something very abstract to something for me very like abstract is wrong word, something a little bit like sort of vague or like something where I wonder about what does it mean? Like we use language to talk about the unity. And now here we still make use of language and we make use of like this nice analysis of it. But it's very nice because like what does it take for your theory of consciousness to explain phenomenal unity? Well, independently of whether the axioms that govern the members, the elements of the set are the axioms of topology or some sort of lattice, let's leave it open for now. At the very least, it's something you can easily get. Like, for example, I think there's a good point to be made that these satisfy the axioms of a topology. And why not? Yeah.
For example, the set that satisfies SUT. And the thing is that SUT is like something that's not well. I mean, if I understand well, it's basically like there's always a set for any sets you can always find.
Well, the any is
You're looking, yeah. So basically, you're saying that you can go for any like you want to build a set of sets in a way. Like this is what's the problem behind. But then you say you're choosing some sets, and you're saying that
no, I'm just saying like here's a statement, and we can say we can say that's a statement about a set X, right? And if that statement holds for X, then X is in your class.
Yeah, but what is this in this case? SUT cannot be referred to from. I mean, like it has to be. But I'm just saying is that here, the way you choose the X's that satisfy this tells something about what it should satisfy, and then there's the structure of what it should satisfy.
No, I think I would put it differently. I would say it like this. There's a phenomenological fact to the matter whether any given X satisfies this statement here. That's something you might not just get by introspection, but you could get it somehow. And then for everyone which does, the corresponding X is going to be in that collection of sets.
But you cannot do it for any, right?
Where's any?
Like the SUT, you do it like, I mean, the set of X such that SUT. SUT could be like X is the power set of itself.
Yeah, there's problems. Yeah.
No, but I mean,
so
then you always weight is on what is a good SUT, or what is a good kind of toe that you constrain, and the thing is you don't attack this problem of
so that's I agree with that. So the question is like, for which X does SUT hold? Like basically SUT holds for X is sozusagen, if we just say we can say SUT holds for X if and only if, right?
Yeah.
And then
if we fix E, say this thing.
Fixed E? Oh yeah.
Stay on the right.
Yeah.
Specific E.
Yeah.
But when you say SUT holds for X, is that relative to?
So yeah, so we have fixed E. Yeah. We talk about this in the paper. Like, though you don't like, and we have fixed E because you don't experience aspects of different experiences. Like when you have a set X that is not part of one A of E, then then it doesn't satisfy SUT. That's a very clear example for why it can't be just all of them.
Is that okay for this claim?
Yeah.
Because you fixed a little E.
Yeah.
So does it make sense? I don't think it's
Yeah,
relative
sure.
to-
Because it's also in here. And in the proof, we can go through the proof. The E pops up in the proof.
Just a question, the claim is AX is an X aspect if and only if. What is the?
So, no.
You say
Um,
AX is an X aspect, then you have X.
That's dot. That's dot. Like, so if I reformulate in this way, we say if SUT, so if you formulate it in this way, now we can say the claim is if SUT holds for X, then, so, wait, so, okay, so SUT holds for X, then we have, sorry, we didn't, no, exists one E, exists one E. Sorry, why it's not exists E like this? Yeah, you have one E for which this is the case. Yeah. Yeah.
Claim or definition?
Claim, and now we can prove it. Yeah.
If SUT holds for X.
So SUT so this is SUT. SUT holds for X if and only if there is an experience such that as the aspects in X are instantiated in the experience. Not okay? Okay. Yeah, okay. Yeah. And then sort of, yeah, this statement holds. And then we can same claim. So let's move the claim up a little bit. I like this version. We didn't do this one in the paper, but I like this. So now we can do it just for every single X. And now what we get then, once we prove that claim, we can say, look, if we just have all the extra in here for which SUT holds, then we get a collection of sets. Now the question is, which axioms does this collection of sets satisfy? That's something that, like, fundamentally, you'd have to consider phenomenology, either by introspection or more likely by doing laboratory operations. The only thing that we can do, or what you do in the paper, is that we say, well, let's speculate a little bit. And at least arguably, it's not a very strong case, but for visual, like when X consists of visual qualia, right? So stuff in vision, not audition, then it's at least likely that this tau satisfies these axioms of a topology. Could be other axioms, who knows?
Topology, you need finite intersection. Infinite intersection. You need to have this, and this is really essential to say what is a point. You need to be able to work out.
What's the problem?
Kind of intersection. There is no notion of locality. At least
no, that comes in because we fix vision. Basically, the idea would be like you take regions and you argue about regions.
So it feels like the
Yeah.
on the left is like a rank.
Maybe could be something else. I'm not married to this idea. Like this part here is the usual sort of, like this is like, let's give arguments. This is not rigorous. Only the white part is rigorous. Yeah. But I think that this is, yeah.
I ask a question. It's kind of a loose language, sorry about that. But when I read this, subsumptive, sorry for my accent.
Yeah.
Thesis and the way it is formulated, I want to translate it in colloquial ways like, oh yeah, the whole is not the sum of the parts. And then you have the problem of mereology problem.
But this is not what it says, I would say.
Any set of phenomenal state of the system.
Yeah, there's just another one. Like there's
each of the states. Yeah, so that's
Yeah,
okay. There is
yeah.
another, but in
But-
this formulation, sorry,
Yeah.
not on the left, not on the sorry,
this one.
not on the
Yeah.
on the white one, but on the yellow one
Yeah.
that you put together as part of an experience. So it seems that X, there is an aspect, so this aspect AX has to be part of a member of.
It's in AE for, yeah.
Yeah.
And you're right, yeah.
So then there is, here we find this.
Infinite
the whole-
regress.
Not
Yeah,
necessarily.
yeah, yeah.
The whole is, it's not just the
Yeah.
set of all.
Yeah.
Of whole,
Yeah.
It's not just the union.
Yeah, you could say,
It's
yeah.
something more. So
Like you could say,
so
yeah.
then-
Yeah. You could say
then
that,
if you
yeah.
want to avoid infinite regress
Mm.
in the context of set theory, and so I'm way out of my league, so I don't master that well, but I wish Ken would still be online, but maybe Grégoire can say something else. You have to give up on the axiom of foundation.
So yeah, so this could be, but what we do here is we just make our life easy, but because we're just saying, well, like it's true for some x, and then basically the rest is just hand waving. Like, I mean, I don't like what I'm.
But you still have to have, even if it's true for some x, these x or those x's, they have to be at the same time the set of all subset and belong to them.
No, they don't have to.
No, they don't have to.
Yeah.
Okay, so that's
Yeah,
where I have
yeah,
a time to
yeah,
see it, but
yeah.
that's my limitation.
No, they just they don't have to because of the way it's set up, right? It's an additional aspect which you get. Question is like from this, like so again, so this is just an example, and I think it's wonderful to make that more precise. It's wonderful to go further. The purpose of that is to illustrate the definition.
But that's super
And
interesting,
as
but,
part of that, the way we took it from here, which I think it says it, is just like you take an X and then whenever you have a set, that's what they say, you get an additional aspect. So that would be the version where you get infinite regress. You can do another version where you say maybe it's not strict subsumption, maybe it's smaller equal, and then maybe you get to these problems with like,
problems or not.
yeah,
You know, I know
or
that
maybe advantages, yeah, yeah,
maybe actually these are not problematic
yeah, yeah,
in some framework.
yeah, yeah.
I mean, it seems like over the top to have to go into like set theory paradoxes in the sense of
Yeah.
you really need the SET to say for any set. Like,
Yeah.
That's so hard to
My-
ground in the hard.
This is exactly
You
what,
just said for any countable set, for any
so this is,
set below.
yeah,
But
Yeah.
then what's the
Zero,
podcast?
something
Yeah.
big, it's still gonna,
yeah.
you're not gonna be able to empirically
This is a,
go
yeah.
beyond that.
This is exactly the perspective we take in the paper. We think it's just like this for any here, it's just too strong.
So can you give us a kind of Venn diagram example of one of those things that would work?
Venn diagram?
A Venn diagram.
Yeah, I mean, think of,
Draw
yeah.
little potatoes and show us an example of that. Is it possible?
Yes. Here's one potato, here's the new aspect.
So, draw little, can that be drawn as a potato?
I don't think so. I don't think so.
No, basically, we said that we.
No, but I don't know what you, like, maybe I'm missing. Oh, you mean for the topology? Yeah. Yeah, sorry. That's over here. Yeah. The question is like, do these things constitute topology? Well, you could be like, actually, this is like, let's do projective geometry a little bit. You know, I don't know much about the topology of projective geometry, but the idea would be like, there's something like visual regions, right? And regions can interact and you can take unions of regions, right? And you can take complements of regions. It's just like literally what you see, parts of what you see.
But where is the aspect of it that captures the?
Well, the aspect thing, no. So the aspect thing happens first. And that gives you the fact that every single one of them is part of a mathematical structure of conscious experience. The whole question, is this a topology or is it a lattice or whatnot, happens second. And that's what you can draw. You cannot draw this, like this is, you cannot draw what it is like to experience, for example, these two hands as part of one experience. I can't draw that as a Venn diagram. Question is, can we represent this at all? And the answer is, yes, we can. And in math, it's particularly, I'm not claiming this example is finished. I'm not claiming that like it's, but we can see that we can, like, it's an example for how we,
Active thinking.
Yeah. But I think actually like the more productive thing to think about, I think it's like, to my mind, like this is sort of nice to have, and ultimately we need to get back to it. But I think the much more interesting question concerns pre-reflective self-consciousness and all the other things we talked about. Like I'm not like, this is one of many ways of understanding it. It's the one I like best. I find it nice. The math is so simple, but let's talk about the things that matter on my view right now.
But
Yeah.
kind of matter.
I think Sean, what he was saying is really, so if I understand well, so the Sean, you were really referring to lattice of like process of a certain topology. And the thing is so the thing is here you have only reunions, so you would have only like uncountable intersection, but you don't have finite reunion. Like you were saying that like for open sets you would have any kind of union for process, any kind of intersection, and I see well like a new concept being the intersection of two process, right? Like, and so you.
Why don't you have that in vision?
What?
Why do you not have that in vision? So I think again about what it means. It means like whenever I have two sets of aspects that I experience as part of so I have one set of aspects, I experience them as part of one experience. I have another set of aspects that experience them as part of one experience. Then the claim is then if they intersect, I experience the intersection as part of one experience together. It's not so far-fetched for me.
But exactly.
Yeah.
You are one directional, like it would have like separate for the U for the
Yeah.
you open only
Yeah.
the union, but close only the intersection, but not at the same time the other way around. Like you don't you don't need a P lattice, you have a semi-lattice.
Yeah, maybe,
So,
but
yeah.
yeah.
That was my instinct when I read like how you would translate it, but I guess
Yeah.
there's just some details in this implication here that
Yeah.
we got.
Well,
How
yeah.
you got topology out.
No. To be very clear, the only implication, so the only thing you get rigorously is the white stuff. The yellow stuff is just like then thinking about it in non-rigorous form. And the only thing you get rigorously is that every single one of them for which the subsumptive unity thesis holds is part of a mathematical.
Let's see, so I think the way to formalize this is in terms of just the process and a join.
Maybe,
Like,
yeah, I
joint
would be open to it.
semi-lattice.
Yeah.
So I don't know, a joint semi-lattice is not.
But why are you saying, I mean, do you have strong phenomenal intuitions about which parts of your phenomenology you experience as unified in that sense? Because I don't. For me, it's very plausible that I can also have like if I have two, like if I experience these all as part of one experience and I experience this one as all part of one experience, it's very plausible for me to think that I experience them both as part of one experience too. Like I don't have strong intuitions that this is not the case. I think my intuition would say, well, it's as far as vision is concerned, it's true for intersection and union. But I wonder, do you have strong intuitions about that?
No, I'm just trying to Sean what you said
Yeah.
really like very like it's
Yeah.
if I understand it well, it's a very good. I mean, it's really marking because it really looks like what you were trying to form, like what you're describing as a property, could resume to simply having a certain kind of concept.
Maybe, yeah, sure.
And then you would say that it's ranked or something a bit more precise.
Yeah.
Don't say that it's unranked.
I think what.
I don't rank is. I don't
Yeah.
think you get ranked from John
Yeah.
saying that this. And then you would because I was thinking about an example, but maybe I'm wrong. I don't remember well the stuff. And then you would fall on something that is kind of standard for it, and then it's clearly not a topology.
Yeah.
Like it's clearly like in many things.
Yeah.
I think topology is a special case. Right?
Yeah.
You said that
But
already,
the
that
interesting,
in this example
yeah.
of the vision.
Yeah. So just I think on the meta level, what I find interesting is that this for me is an example, a very early one because we still rely on language very much, but an example of where you can do mathematical phenomenology and really get sort of like tie yourself loose from the constraints of language. And like, for example, the interesting question for me is like, let's say it is a topology in a special case. Then the funny thing is like now you can actually can think about what does it mean? Like what does a topology bring myself? Like what does closeness have to do with phenomenal unity? Maybe the answer is I think it doesn't and it's shit and we should rethink the start. But my feeling is like generally speaking, independently of that case, the interesting question is whether these things afford new perspectives or new connections. Yeah. And that too. Yeah. 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 Yeah, I think so too. Yeah.
No, but
Yeah.
it's not really about maths. Just they capture in a bit like I feel that what you were trying to do with the description is try to say what would be the structure of things that satisfy SUT. What does it look like in general? Something that has SUT, right?
Yes,
What you want to try. Yeah.
Yeah.
And this makes sense, and not makes sense, but it's not what I was saying.
Yeah.
I would say it's just like in maths, what you try to do is what does it mean? How to make sense of things that are close. And then you get a very rich description of it.
Yeah.
Like topology and everything.
Yeah.
And then, for example, what it is to have stuff is sets.
Yeah.
Right? Sets tells you how to what is constituent of something.
Yeah.
And then, but these are ideas you can formalize, and they became extremely general.
Yeah.
And the thing is that maybe what you were describing here already relates to something that
Maybe.
exists.
Yeah.
And in this case, I mean, like it makes it more.
Hmm?
So what I want to say is you have an idea and then you get a general way to describe it, and this applies in a very large amount of context. And sometimes you get another idea, you realize the formulation is the same, so the two ideas are very related, but it can be the same, right? But I mean, like it's just like what idea do you want to capture? Like if you want to capture SUT, for example, or are you trying to just to say like I want to find the structure of a certain idea that appears in phenomenology, and I realize that the mathematical concept can instantiate it correctly, and maybe it doesn't exist. Maybe it
Ultimately, so for me, the ultimate goal is to try and sort of do this primitively, meaning like maybe we can literally like work right off the start with math. But for the time being, just initially, this is very at the beginning, I do basically this, it's the same sort of thing that I think everyone is doing. Like you start with some sort of description of phenomenology in words and think about how that would translate into math. What the claim or the idea behind that research, or the hope, is that we can go a step further than just using analogy and intuition, right? Like,
Very clear.
yeah, and yeah,
And
and,
the way you
yeah.
analyze things. I mean,
Yeah.
But in this case, you need language. Like you need
Right now,
language and very well. You need to be extremely. Like the most.
But maybe not
difficult part of math
ultimately.
Is to create. Is to create.
Oh,
things.
mathematical language. Yeah, sure.
But
Yeah.
yeah, but you need form, like formal
Yeah, that's what I mean.
statements.
Yeah, sure.
You don't
Yeah.
necessarily think formal statements that already exist.
Yeah.
But at least you need to
Yeah.
make the things
But like,
very formal.
so for example, to go back to this initial paper by Maxwell Ramstad and Anil Seth and others, like, do I need the Husserlian concept of Hülle and Neumann to make sense of the way that objects are constituted in experience based on raw sensory data? My intuition would be probably not. Like probably we can replace these concepts by something that fits precisely and that makes sense in light of these concepts. Maybe that's what Thomas Metzing always says about computational phenomenology. I think the idea he has in mind is basically like when someone tells you the structure, you're like, it must be that. And maybe that works for some cases, maybe not for others. But the idea would be like we can basically that's what I meant with math is precise and flexible. We can craft math in such a way that it picks out the exact content of Hülle that we need for the phenomenology here, while leaving other contexts, which are maybe more metaphysical, to the side.
Yeah, but at the same time, when you think about Husserl, very broad production, and all the pages that have never been read, basically.
Yeah.
I mean, of course, we have to make justice to that. I think
Yeah.
he's trying to capture something, that was much richer than just the reductive concept of Hülle.
Of course, yeah.
At the same time, there is this paradox in Husserl, and again, I'm a bit out of my league, but is that he was a mathematician, but by training. But nevertheless, maybe for metaphysical reason, he never.
I heard about that.
Have very well, because he was equipped to do it. Move to use math to do exactly what we are discussing today, instead of writing these kilometers of pages with very long.
I think that.
What do you think? Why do you think?